Hello, welcome to AP Calculus Lecture 5.7a, where we're going to talk about differential equations again, but this time instead of finding just the general solution, we are going to find a particular solution or a solution at a point. So let's just go through some examples. Let's say we have dy over dx is equal to 3x over 5y plus 1. So we want to separate the variables like we did in section 5.6a. So we're going to cross multiply, and I'll have 5y plus 1 dy is equal to 3x dx. Now we'll integrate both sides, and the antiderivative of 5y, you're going to go from y to y squared, but you'll need a 5/2 out front. The antiderivative of 1 is not 0, it's y. And then the antiderivative of 3x, we're going to go from x to x squared, and then I would need a 3/2 out front. And then we only need one c, so we'll put the c over here on the right side. Okay, just double checking to make sure I did this right. 2 times 5/2 is 5, then 2 minus 1 is 1, so you get that. Derivative of y would be 1, and then 2 times 3/2 would be 3. Subtract 1 from the exponent, you're back up to 3x. Okay, this is what we called the general solution. But what if we wanted to get a particular solution at a given point? So let's try to find the particular solution given y of 1 is equal to 2. So that would be 1 would be the x value, 2 would be the y value. Or you might see it listed as something like this, 1, 2, at the point 1, 2. Okay, so we're just going to substitute these numbers right up into our general solution and solve for c. So we'd have 5/2 times 2 squared plus 2 is equal to 3/2 times 1 squared plus c. So 2 squared is 4 times 5, that'd be 20 over 2 plus 2 is equal to 3/2 plus c. So that's going to be 10 plus 2, 12, and then bring the 3/2 to the left side, so minus 3/2 equals c. 12 is the same as 24/2, or 24 over 2. 24 times 3, 24 minus 3 would be 21/2. So we can rewrite the particular solution as 5/2 y squared plus y is equal to 3/2 x squared plus 21/2. That's our particular solution. Of course, the book might, a lot of times the book will bring the x to the left and then set it equal to the constant. Doesn't really matter to me. It's easy to manipulate to get to whatever answer, whatever way the answer is portrayed on a multiple choice situation on the test. All right, that's our first example. Let's do a few more. So let's solve. Again, differential equation is just an equation that has a derivative in it. So dy dx is a derivative, is equal to e to the x minus y. All right, that looks kind of difficult, but if you can rewrite it, e to the x minus y is the same as x minus y, the same as division, e to the x over e to the y. So that is the same as this. Now it's easy to separate the variables by cross multiplying. You'd have e to the y dy is equal to e to the x dx. Now we will integrate both sides. And the antiderivative of e to the y is just e to the y. And that's going to be equal to e to the x plus c. So that's our general solution. Let's find the particular solution at the point, how about 0, 1? So the particular solution at 0, 1 would be e to the 1 is equal to e to the 0 plus c. So e to the 1 is just e to the 0 is 1. So c is equal to e minus 1. So going back up to the general solution, we could write this as e to the y is equal to e to the x plus e minus 1. And that is the particular solution at this point. All right, you don't want to get your x and y backwards, so be careful with that. Okay, I've still got several examples to do for you. Next one, we're going to look at the book on page 34. Excuse me, number 34 on page 374. And it says just to find the general solution. So we're not given a point, so more practice on general solutions. We have dy dx is equal to x times the cosine of x squared. Separating the variables is easy. We would just multiply both sides by dx. And then we're going to integrate both sides. So the antiderivative of dy is y, but we're going to need to do a u substitution on this integral. So let's let u be x squared, because we want to pick a u that if you take the derivative of it, the derivative is sitting in the problem. So du would be 2x dx. That's almost what we need. We need it to be x dx, right? So if we divide by both sides by 2, we'd have 1/2 times du is equal to x dx, which is exactly what we need. So we can rewrite this as bring that 1/2 out front, and you'd have cosine u, because u is x squared, times du. So the antiderivative of cosine u is just sine u. So we need to substitute back in for u. We know that u is x squared. So we can say that y is equal to 1/2 sine x squared plus c. So that is our general solution. And of course, if we were given a point, we could plug in and get the particular solution. All right, that's a good one with a u substitution. To remind you how to do that, did a lot of that in chapter 4. Okay, we've got 2 more to go. Let's look at example 50 on page 374. So example 50, this is find the particular solution. And we have the square root of square root of x, plus the square root of y prime, let's write that as dy dx, is equal to 0. And our initial condition is y of 1 is equal to 4. Okay, so first of all, we can separate these variables by multiplying both sides of the equation by dx. That would do the trick. If we multiply both sides of the equation by dx, you would have the square root of x dx plus the square root of y dy, because dx over dx cancels, and anything times 0 is 0. So there you go, just that one trick. We had to do it to both sides. That one trick of multiplying both sides by dx, we separate the variables. Let's go ahead and we'll put the x to the right side. I'm going to rewrite this as y to the 1/2 dy is equal to negative x to the 1/2 dx. And let's take the antiderivative of both sides. So that's going to be y to the 3/2, but we'll need a 2/3 out front, is equal to x to the 3/2. We'll need a 2/3 out front and make it negative, plus c. So that is our general solution, but we have an initial condition. We need the particular solution, so let's plug in 1 for x and 4 for y. So we'd have 2/3 times 4 to the 3/2 is equal to negative 2/3 times 1 to the 3/2 plus c. Square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. So 16/3 is equal to negative 2/3 plus c. So if we add 2/3 to both sides, 18/3 is equal to c, and that's just 6. So our particular solution would be 2/3 times y to the 3/2 is equal to negative 2/3 times x to the 3/2 plus 6. And I believe the book pulls this negative 2/3 x to 3/2 over to the left and makes it positive, sets it equal to 6. Doesn't really matter. You just need to be able to match up your answer to a multiple choice option. So you may have to move some of your variables to the left or the right of the equal sign. All right, one more to go, and then I'll give you your homework for this lecture. Not really a bunch of new stuff in this lecture, but it is an important lecture, as you could in college have an entire class, or maybe even more than one, on differential equations. Our last example is 41. So this is on page 374. So 41, we're finding the general solution again. I wanted to give one of these to remind you how to write a solution like this. So we have dr over ds is equal to 0.05 r. So what I want to do is separate these variables by divide both sides by r, and then multiply both sides by ds. So that'll move the ds to the right, and that'll bring that r over to the left. So you can double check me if you want, but this and this are the exact same thing. Okay, and now you have an easy integration on both sides. I think it's easier because ds is an easy integration. Let's leave the constant on that side instead of bringing it over here. You'd end up having 20 dr over r. Let's not complicate things by having that constant with that natural log. So you'd have the natural log of the absolute value of r is equal to 0.05 s plus c. Now we don't want to leave it like this. We want to exponentiate both sides. So that's going to be e to the natural log. I'm going to go ahead and get rid of the absolute value, is equal to e to the 0.05 s. 5 and s look similar, so sorry about that, plus c. And now e and natural log cancel each other out, and you have r is equal to e to the 0.05s times e to the c. Remember us doing that, where e to the c is just c. So r is equal to c e to the 0.05s. And that is the way you need to write that general solution. So I want to remind you how we exponentiate and how we bring that constant out front and make it a c, which we of course have done quite a bit already. So your homework is on page 374. That's where it starts. And let's do 33, 35, 43, 47, 49, 52, and 55. So that'll be a good practice for both particular and general solutions. So I hope this homework goes well for you, and I will talk to you on the next one.